Hello everyone, today we are going to learn about curve sketching. So that corresponds to 4.5 in your Nelson textbook. So when we are sketching a curve, we need the following information. X and Y intercepts, we need asymptotes, we need critical points using the first derivative test, we need points of inflection using the second derivative test, and finally we are going to sketch the graph using these information. Let's start with the first example. F of x equals x to the power of 4 minus 3x cubed. So we said we need x-intercepts. To get the x-intercepts, we need to factor the original function. So x cubed is a common factor, and we get x minus 3 as a second factor. Then the zeros of the original functions are 0, 0, and 3 and 0. Then we need to get the y-intercept. To get the y-intercept, we substitute 0 for x in the original function. So we get 0. Then we need to write the asymptotes. But since this is a polynomial function, it has no asymptotes. Okay, now we need to get critical points. To get critical points, we need to take the derivative of the function. Then we get 4x cubed minus 9x squared. When we are doing the first derivative test, we use zeros of the first derivative plus the values that make first derivative undefined. In this case, actually, since it is a polynomial, again, the first derivative function is a polynomial, there is no value that makes it undefined. So we are just going to use the zeros of the first derivative for our first derivative test. In this case, x squared is a common factor. We get 4x minus 9 here. So zeros of the first derivative are x equals 0 and x equals 9 over 4. So you can also get the decimal value of it, which is 2.25. Again, in our table, we are going to use those zeros, 0, 2.25. Now we need to check the sign of the first derivative. So pick a value in each interval, sub them in the first derivative function to get the sign of the first derivative. So in this interval, from negative infinity to 0, we can pick, let's say, negative 1, sub in here. As you see, x squared is always positive and it is not affecting the sign of the first derivative. So I'm just going to sub the value here for x minus 9. So negative 1, sub in here, you get negative value. Pick a value between 0 and 2.25, let's say 1, sub in here, you get again a negative value. And for this interval, we can pick 3, sub in here, you get a positive value for the first derivative. It means original function is decreasing, and increasing. So, as you see, the function is changing from decreasing to increasing at 2.25. Therefore, we have a local mean point here. X value of that local mean is 2.25. To get the y coordinate of that point, take 2.25, sub in the original function. So that gives you negative 8.54. Now the question is also asking you to write increasing and decreasing intervals. Increasing from 2.25 to positive infinity. Decreasing, so from negative infinity to 0 and from 0 to 2.25. You may be wondering why we are not taking 0. As you see, if we substitute 0 on the first derivative function, we get a 0. So first derivative is not negative. Therefore, original is not decreasing at 0, but we just have a horizontal tangent at x equals 0. Now let's do the second derivative test. So to be able to do that, we need to take the second derivative. First derivative was 4x cubed minus 9x squared. We're going to take the derivative of that. So we get 12x squared minus 18x. To be able to do the second derivative test, we need the zeros of the second derivative plus values that make second derivative undefined. But in this case, again, there is no value that makes second derivative undefined because it's a polynomial. Therefore, we are just going to take the zeros of it. So 6x is a common factor, so we get 2x minus 3. So zeros of the second derivative are 0 and 3 over 2. Decimal value 1.5. So we use those values in the table. Now we need to check the sign of the second derivative. So pick a value here from negative infinity to 0, let's say negative 1. Sub in, check the sign of it. So here we get positive, pick a value here, 1, sub in, we get negative and positive. So f is concave up from negative infinity to 0, down from 0 to 1.5, and concave up again when x is greater than 1.5. As you see, function is changing from concave up to down at 0, therefore we have a point of inflection here. And at 1.5, function is changing from concave down to up, we have another point of inflection here. So let's calculate the y coordinates of those points. Take 0, sub in the original function. You get 0. Take 1.5, again, sub in the original function. You should be able to get negative 5.06. You can also write concavity intervals for concavity. So let's start with that. So concave up. So we need to write where the function is concave up from negative infinity to 0, from 1.5 to positive infinity. So negative infinity to 0 and from 1.5 to positive infinity. Concave down from 0 to 1.5. Next step would be combining first derivative test table and second derivative test table to check the shape of the curve in each interval. So when we are combining, you need to take those values from the first derivative and second derivative. So we have 0, 2.25, 1.5, put them in order from smallest to largest. Okay, let's look at the first derivative table first. So between negative infinity and 0, f is decreasing. Between 0 and 2.25, it is still decreasing. And when x is greater than 2.25, it is increasing. Now let's look at the second derivative test table, and we see from negative infinity to 0, f is concave up. Between 0 and 1.5, it is concave down. When x is greater than 1.5, it is concave up, concave up, concave up. Now, to see the shape, we can again look at the phase that we learned in 4.4. In this interval, so in this piece, if the function is increasing and concave down, we use that shape, decreasing and concave down, increasing and concave up, decreasing and concave up. Okay, so based on that, if we combine, so first one is decreasing and concave up, look like this. Okay, here decreasing and concave down, it should look like this. Between 1.5 and 2.25, decreasing concave up, decreasing and concave up. It should look like this. And finally, when x is greater than 2.25, increasing and concave up. So it should look like this. Now let's sketch. First I'll draw x and y axis. Let's put our x and y intercepts 0, 0 and 3, 0. Y-intercept is again 0, 0. We already put that point in our graph. Let's put local minimum. It is happening at 2.25 and negative 8.54. Let's also put our point of inflections. We have one here, 0, 0. And then we have another one at 1.5 and negative 5.06. Okay, we said that when x is between negative infinity and 0, the shape of the curve should look like this. Between 0 and 1.5, it should look like this. Between 1.5 and 2.25, it should look like this. And when x is greater than 2.25, it should look like this. Please go to part 2 for the second example.